Carboxylic acids contain the functional group COOH. You'll see this written on the end of the molecule as COOH in a structural formula, and this signifies a carboxylic acid. So for the very simplest of carboxylic acids, we have methanoic acid. Methanoic acid is formed by the further oxidation of a primary alcohol from its aldehyde methanal to methanoic acid. So one of the preparations we'll look at later on is how you can further oxidize a primary alcohol through its aldehyde stage into a carboxylic acid. Once again, just like with aldehydes and ketones, because the carboxylic acid functional group is part of the main chain, we have to therefore count that as carbon 1. It will always be on the end, just like an aldehyde. Therefore, in the molecule just here, the bromine group, or bromo, would be found on carbon 3. So overall, this would be 3-bromo butanoic acid. If we were to write out a structural formula for 3-bromobutanoic acid, once again we take each carbon at a time, CH3, CH, Br, CH2, COOH, and that would be the structural formula. If we were to add things like amino groups or hydroxyl groups, so NH2 or OH, then we would have those at the start also, labeling them in alphabetical order. I'll give you an example now. Now, if we were to draw this molecule out, we simply take each carbon at a time. So the first carbon, CH3. The second carbon is CH with an alcohol group attached. Third carbon, CH2. Fourth carbon, CH with an amino group attached. Fifth carbon, CH2. And the final carbon is our carboxylic acid functional group. So in order to name this, we have to have the carboxylic acid group as carbon 1. That means to say that our amino group is on carbon 3 and our hydroxyl group is on carbon 5. So overall, the full name for this molecule will be 3-amino 5-hydroxy hexanoic acid. Notice that the functional groups have been put into alphabetical order. Preparation is from the full oxidation of a primary alcohol. Now this will go through the aldehyde stage before it gets to the carboxylic acid, but overall we're preparing it with the oxidation of a primary alcohol. For example, let's take something very simple as ethanol, and we're going to make it into ethanoic acid. Now what we need to do is, as usual, balance this as a redox half equation. So this time we actually do have water to add, as there are 2 oxygens on the right hand side and only 1 on the left. We then add hydrogen ions to balance which side is deficient of hydrogens. So we have 4 on the right, and we have 3, 4, 5, 6, 7, 8 on the left, so we need 4 hydrogen ions. That should be 8 on both sides now. Therefore we need 4 electrons. We could then oxidize with our, say, permanganate ion. This time you'll notice that both equations have to be multiplied, the top one by 5 and the bottom one by 4, and this will give us the overall equation. Okay, so in this equation, if you remember back from the redox topic, we can cancel hydrogens and waters by removing the least amount from each side. So with the water, there are 5 waters on the left hand side and 16 on the right, so I'm going to remove 5 from each. We can do the same with the hydrogen ions. There are 32 on the left and there are 20 on the right, so I'm going to remove 20 from both sides. And we can now rewrite the whole equation to show what we've done. I suggest you do this on a bit of scrap paper or at the back of an exam before you write out your whole equation, just to make sure you've got plenty of room to work it out. Carboxylic acids have an OH group and a C double bond O group. Due to this, they can form strong hydrogen bonds. As a result, carboxylic acids for similar molecular sizes have got the highest boiling points and densities of all organic molecules. In the example above, we can label the polarity. Each of the carbons here has a delta positive, each of the hydrogens is delta positive, and each of the oxygens is delta negative due to their electronegativities. We can then show that there are strong hydrogen bonds formed between the molecules, signified here by the magenta line, the dotted line. These are hydrogen bonds. This means that the molecules are held quite strongly together when they're in close proximity to each other. In the diagram above, you'll notice that the two molecules are almost turned 180 degrees with each other. These are also known as dimers. Which will make more sense later on when we look at polymers. Di meaning two, mer is to do with the molecules joining together. The other properties of carboxylic acids are they are weak acids. So if we take ethanoic acid and react it as a Lowry-Bronsted acid with water, we have to show it's a weak acid using the equilibrium arrows, and we go to make the ethanoate ion and our hydronium ion. Because it's a weak acid, it also undergoes many reactions just the same as any other acid. For example, if we were to react ethanoic acid with a metal such as magnesium, it would go to make hydrogen a magnesium ion and the ethanoate ion, which we leave separate because they're both aqueous. Of course, the carboxylic acids will react with carbonates to produce a salt, water and carbon dioxide. They'll react with metal oxides to produce salt and water. They will undergo most traditional acid-base reactions.